this is working. So, today we are starting chapter 5. More importantly, we're actually kind of starting the second half. We're like going downhill now. So, remember we talked at the very beginning of the year, we had derivatives and we had, and that's what we're starting today, antiderivatives. So, the other good news is, just like at the very beginning of doing derivatives, they were easy. Remember, you look back to like day 1 of derivatives, take the exponent, multiply it by in front, subtract 1. Remember how easy that was? Well, the beginning of integrals are easy like that too. Okay, and then they'll slowly get harder and harder, but we're not going to worry about that right now. So, we are, this is notes number 15. 5.1 antiderivatives. Page 336. Okay, so just to begin with, an antiderivative is just what we just talked about. Think of it this way, it's the inverse operation of the derivative. Okay, this is also called, so it has another name, and we learned this at the very, well, you probably don't remember, it was a long time ago. It's also called an indefinite integral. Okay, indefinite integral. There are definite integrals and there are indefinite integrals. So specifically, an antiderivative is an indefinite integral. But you'll use it. I'll use it all the time. You can more or less use the term antiderivative and integral interchangeably. Okay, we're just talking about the same thing. So we're just going to think backwards. Now, first of all, the symbol, the notation. If I want to take an antiderivative or an indefinite or an integral, would look like this. So you have the symbol actually consists of two symbols in one. They're like bookends. You have to put parentheses. You have to put them around the expression that you want to take the antiderivative of. So these two symbols, this long skinny s and the dx together, they indicate that you want to take the antiderivative of everything in between. So this is the symbol here. Okay? Think of that together as a symbol. This stuff in here, this is called the integrand. So when you use it, it turned out too good. Integrand, R-A-N-D. So when they talk about the integrand, that's just the stuff that you're taking the integral of. It's the stuff inside those two symbols there. All right, and then another question, another symbol you can think about. People let's think about, well, if I took the integral of f of x, what do I call that? Like, what do I use for symbol? And so typically we designate a capital F of x to indicate the antiderivative. Okay, but don't get too all excited about that, because like on your homework people say, how do I label all these? How do I label these? Well, just write down the answer. If they said, find this, then you're just going to write down what it equals. You don't have to worry about the notation or label or something like that. But in general, capital F is typically reserved for antiderivatives. So if you think about it this way, f prime, capital F prime of x, so if you take the derivative of this antiderivative, you should go back to the original function, f of x. That's another way of thinking about the connection between the two. Alright, so this is all warm-up stuff, just in general, get an idea what the symbols are going to look like. Let's do a problem. So, the integral of 3x squared minus 4x plus 2 dx. Alright, what do you think? Just think backwards in derivative. What are you going to do? Add 1 to the exponent and then divide by the new exponent. Make sure you divide by the new one. Okay? So you're going to add 1 to the exponent. I'll write this out for you so you have it down. Add 1. Oops. 2 add 1 to the exponent, and divide by the new exponent. So if we're doing this on the homework, you would simply go along, you'd add 1 to the 2, so you get x cubed. You would divide by 3, so now you have x cubed. Add 1 to this x, it's x squared, so now we get minus 2x squared, plus, what's the antiderivative of 2?
2x.
2x, right? And again, think of the derivative. The derivative of 2x is 2. And now you're not quite done. Yeah, we need a constant here. We call this the constant of integration, plus c. Why do we need plus c? Well, what do you think? Now think about it. Why would you need plus c? Bailey, why do you need plus c?
If you took the derivative of the number without moving x to the 0, then it would just become 0.
Okay. You got a good start. Riley, what were you going to say?
Yeah, I was going to say like any number without a variable and take the derivative of it and just cancel out with 0.
Right? So you guys are kind of saying the same thing. So therefore, there could have been a whole bunch of answers to this, right?
Yeah.
You could have had plus 1, you could have had plus 10, you could have had plus 1,768,000, you could have had plus e, you could have had plus 0. Those are all possible answers to this. So that's why we write plus c, because if we take the derivative and go back, the derivative of this number, regardless of what it is, would be 0 and be gone. And this is why we call this an indefinite integral. Now you can see why it's called that, an indefinite integral. How many solutions are there?
Infinite.
Yeah, an indefinite number of solutions. You got the idea? That's why it's called an indefinite integral. Okay? So, that's the power rule. That's how you do a lot of them. In general, just remember, so there's, again, it's not all power rules, but in general, think backwards. A little tricky at first. Takes a while to get used to it. Somebody says, "Oh, I'm getting a lot better after doing a few of them," because you're so used to thinking forwards, doing derivatives. Now you got to think backwards. Okay, so think backwards from the derivative. For example. Rip off a whole bunch of them here. So I'm going to write them down. You're going to try to write them on here, what you think it would be, and then we'll see if you got it right, okay? What do you think about this one? Taylor already said, oh no, not e to the x. Yeah, that's so hard to remember that derivative, isn't it? It would be 3e to the x. Now, first of all, this 3, don't let that 3 bother you. What is that 3?
Little brother.
Little brother. So you could rewrite it like this. That's really bugging you. Stick it outside and ignore it and just take the integral of what's left. The integral or antiderivative of e to the x is e to the x, and then stick the 3 back in when you're done. So it's this 3e to the x plus c. This one. All right, what's that one? You got it. You got it. So this is one you've memorized. Don't forget your plus c. What would the integral of sine of x be, though? Say it again. It is negative. So be careful of that, because we're talking about the antiderivative. So the derivative of sine was positive cosine. But think about going backwards. The derivative of cosine was negative sine. So the antiderivative of a positive sign would have to be a negative cosine. So this is negative cosine. It's going to be tough at first because you're so used to doing derivatives, and then you get used to doing antiderivatives, and then we'll throw derivatives back at you, and then you'll be completely confused because you're going, don't know which way to go, but we'll survive, okay? So, again, if I would have had, let's see, let's do another one. Hold on, let me try this one first. Let's try this one. What'd you say?
I said, oh god.
That would be the square
I
root.
don't know if praying's going to help at this point. Do you know this? Do you know any derivatives that have an answer of secant of x?
Secant squared.
Do you know any derivatives that have an answer of secant? No, you don't know this yet.
Is it really long?
Yet, okay?
Oh.
That's the important thing. Yeah, you're going to learn how to do that. But for right now, we're just focusing on the ones you know backwards. All right? So that you don't know. However, what would that be? Yes, you have this memorized. The derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. And the 5, just a little brother. So it's 5 tangent of x plus c. I'm going to go to another page. We're going to do some more here, but otherwise this page will be very long. Okay, let's try this one. What is it? It is. All right, so that's a special one you've got memorized. That's the natural log of x plus c. Now, don't forget, it's always interesting because then people get this question. And then they'll panic and think, what do we do? I added 1 to the exponent and I got 0 and I divide by 0, it's undefined. Yeah, so that should clue you in that you're going down the wrong path here. Don't be fooled by this. This is just the same as 3 times 1 over x. So what is the antiderivative of that? Okay. Now I'm going to add one little tiny thing to this because this is it seems picky, but this is important. You cannot take the natural log of a negative number or 0. So what you'll see often is that when you write your answer, they're going to expect you to put absolute value around this x because they want you to know you can't take the natural log of a negative number. Okay, so just kind of be leery of that. All right. How about this one, though? Do you know any? What do you think, Brent?
Just 1 over x.
A lot of people think that, but that would be the derivative ln of x is 1 over x. So the antiderivative ln of x isn't 1 over x. Do you know any answers to any derivative problems where the answer is ln of x? No, not yet. By the way, I'm not going to give you any of these on the homework, so you don't write down. None of the answers to the homework are not yet, okay? You can do all of the ones I'm giving you on the homework. Because people are doing that. They're like, oh, this is a not yet one. Like, no. You know this one.
I don't know any of them.
Oh.
This is not a not yet one. You know this one. You're supposed to know this one.
Oh, wait,
yeah,
not
inverse.
Inverse something, right?
Sine.
Not quite. Tangent. Inverse tangent. So, inverse tangent of x plus c. This is why it was important to have them all memorized. All right. Then you're going to get some that at first you think you can't do them, you don't know how, let me show you this first one right here. Okay, so you get a problem like that. This throws people off all the time in the AP test, and these are actually quite simple, but people look at that and they get confused. Because first of all, there's no quotient rule for integrals, there's no product rule for integrals, there's none of that stuff. You're going to learn some, don't get too excited, there are rules, but there's no quotient rule or product rule, okay? There's a chain rule, there's other things. So, you don't do low D high minus high D low or anything like that on here. What you want to do is you want to simplify it first. If you just have a t cubed underneath here, that means each of these quantities need to be divided by t to the third. So I would write it as t, or 12t to the 8th over t cubed minus t over t cubed dt. Which would be, and I haven't taken the integral yet, of course, 12t to the 5th minus t to the negative second. When you're doing antiderivatives, it's best to just have exponents, including negative exponents, because you're going to add 1 to the exponent and divide by the new exponent. So now I get the antiderivative, add 1 to the exponent and divide, so I'm going to get 2t to the 6th. If I add 1 to negative 2, what do I get? Negative 1, right? Be careful, not negative 3. So I'm going to divide by negative 1, so it becomes plus t to the negative first plus c. Here's another one that throws people off. So like I just said, at right now, at this point, there's no, well, there isn't any product rule at all. So if you had something just like that where you multiply two things together, you would just go ahead and multiply that binomial together. You get x squared minus x minus 12. And then you would use the power rule. So you get 1/3 x cubed minus 1/2 x squared minus 12x plus c. Okay, how are we doing so far? Questions with that? So, this is all the same topic here, but the next thing they talk about in the chapter is this idea of differential equations. And they talk about it as an introduction to differential equations. And a differential equation sounds complicated, but it's not. It's just simply when you have the derivative, like dy dx equals something. So everything you've done up to this point in your math career, the equations have always been a variable like y equals something, or x equals something, or t equals something, or x plus 2y plus 5, you know what I'm saying? Now we're going to be given, you already have been doing problems where you're going to start with the derivative equals something. You're given a derivative, or in other words, you're given a rate. You think of it that way in terms of an application. And you want to solve it. And by solving it, we mean, so to solve a differential equation, you take the antiderivative to find, and I'll just say y equals, or whatever, it could be a different variable, of course, but you want to go back to the original equation. All you future engineers, you have to take an entire semester of differential equations. We call it DiffEQs for short. And there's a lot of problems, because they're applications. If you think about it with rates, I really enjoyed it. A lot of tank problems, this tank's leaking and this hole, and water's pumping this one, then it's got a pipe coming out of this end, and something else is happening here, and you got to look at all those rates and try to solve those differential equations. So let's show you how. I mean, it's pretty. I won't say easy, but it depends on the problem. But at first, they're going to be pretty easy for you. So let's say, for example, we have dy dx equals 2x plus. Oops, I don't want that. Dy dx equals x squared minus 2x. Okay, and if they say solve the differential equation, that just basically means find y. And y would be the integral of this. So we use our power rule, we add 1, the exponent, and we got 1/3 x cubed minus x squared. Don't forget the plus c. So that is our equation. Now, of course, there's an infinite number of solutions because of the plus c. And sometimes that's all they want. But sometimes they'll say, okay, we want to find the particular solution. And they'll say when, maybe for example, f of 1 equals 1/3. So what that means is you want to solve for c given a point. They have to give you 1 point. If they can give you 1 point, you can plug that point in and then you can find the c value that would work for that point. If you think about this plus c, if you graphed out all the equations plus c, you'd have all these equations look exactly the same, but they would just be through different y-intercepts. You know what I'm saying? They kind of be stacked on top of each other. There's probably a graph in there we can look at. We're finding the one particular solution that goes through this point. So just in general, I want to make sure you understand in terms of notation, if this is y equals, of course we can use function notation and say f of x equals that. Well, that's all equivalent. And if they say to you f of 1 is 1/3, I think that's what I said, that's the same thing as saying the point 1 comma 1/3, all meaning the same thing. So all we want to do is plug in the value, 1/3 in for y, plug 1 in for x. We would get 1/3 equals 1/3 minus 1 plus c. To get c is equal to 1. So your final answer, your particular solution, would just be 1/3 x cubed minus x squared plus 1. Okay, and again, you can only do that if they give you a point. Alright, now we're going to do one more example, and this one will be more of an application one. It's a common application, as you know, is physics stuff, acceleration, velocity, position. This example is on page 345, number 9. So this is applications. With acceleration, velocity, and position. Now, before we get into the example, let's just kind of quickly review. If I start with acceleration, how would I find velocity if I start with acceleration? What do you think? And we're thinking backwards now, so what would you do? Antiderivative, right? So velocity is the integral of acceleration. And then if we wanted to get to position, we would take the integral of velocity. So the position is equal to the integral of v of t. right? So we know that connection already. Now we're just going backwards from before. So for example 9, on page 345, they give us a whole bunch of information. It says, neglecting air resistance, motion of object moving vertically along near Earth's surface, so up and down. You got this object thrown up in the air, up and down. It's only the acceleration is due to gravity, so you have the acceleration is 9.8 meters per second, or excuse me, meters per second squared. So in other words, they're telling you, here is your acceleration formula, negative 9.8. They're also giving you the stone that you're throwing upward at t equals 0. So when t equals 0, you get a velocity of 40. So that's telling you v of 0 equals 40. And they don't have to actually give you the initial. I know like in physics they always give you the initial velocity, which they're doing here, but they wouldn't have to. They could give you any point, any velocity at any time. And you could solve for c like we did before. And then it also says the height that's being thrown up, it's starting at that time 0 of 100. So the position, because we like to use s for position, we like to be different in calculus, you get 100. And then they say find a bunch of stuff. They say, let's take a checklist here. Find v of t. Find s of t. Find the maximum height, and find the speed when the object hits the river. Well, that's a little tricky. When it hits the river, what do you know? What's going on in the situation? Height is 0. So speed at height equals 0. Alright, so v of t. So what we're going to do, we're going to dig through our folder, find all our physics formulas, and start writing everything down?
No.
No! We're going to use calculus. V of t would equal the integral of a of t. I'll write it all out here so you remember. So v of t is the integral of negative 9.8. What is the antiderivative of negative 9.8? 9, yeah, this isn't a trick question. Sometimes the easiest ones are the hardest. It's just enough. Oh, I forgot that. That's why you're looking at me weird. I forgot the D in front of my T. Sorry about that. Oh, by the way, don't forget these DTs or DXs. A lot of people, last hour, they were whipping along, they were writing this out, and then they just didn't think you needed to write that, because as long as you had the skinny S, everything was good. No, this is part of the symbol, so make sure you write that. What is the antiderivative of negative 9.8? Why are we so afraid to answer that question? Negative 9.8 t plus c. That's it. That's the antiderivative. That's our velocity equation. Now, we want to find for this specific situation, they gave us one value, 0, 40. We're going to plug that in to solve for the c value, negative 9.8 times 0 plus c. And you get c equals 40. C will not always be the value that they give you. You got to plug it in and find out, especially when you start getting e to the x or something like that. This problem, the thing about it is you look at it like, oh, I could have done this in my head because I memorized this formula. Yeah, it's kind of cool to see how it works out, but trust me, there is a whole variety of equations, so you're going to have to go through this process. You won't be able to just do it in your head, okay? So we get that. V of t equals negative 9.8 t plus 40. There's my velocity equation. All right, we accomplished our first task. Position. How am I going to get the position? Antiderivative of that. S of t is equal to the integral of v of t. So it's good to show what's going on here. S of t equals the integral of negative 9.8 t plus 40 dt. Integrate. S of t equals negative 9.8 divided by 2, 4.9. T squared plus 40t plus c. And again, they gave you a value to plug in. We're going to put 0 in for time and 100 in for the height. And you're going to end up with 0, 0. So C is 100. So my final equation for the position at any time is negative 4.9 t squared plus 40 t plus 100. And again, they didn't have to necessarily give you the initial time. They could have given you any position at any time and plugged it in. And now it's cool because you have these equations. You can find the height at any time. You could find the velocity at any time. You could find the speed at any time by taking the absolute value of the velocity. We want to, for our next task here, maximize the height. Well, we just got done doing min-max problems. How do you maximize something? First derivative, yeah, you think you're going to be able to forget the first derivative test? No, you're probably going to see it on every single test for the rest of the year. Because mins and maxes, you're going to see it all the time. So we want to maximize height. We want to take the derivative of height, or position in other words. What's the derivative of position? Yes, so we're going to take this problem right here, negative 9.8. So we're going to take v of t, negative 9.8 t plus 40. And we're going to set it equal to 0, and we're going to solve, and we're going to find t. And when they did that, just to save us some time, we'll look in the book and see what they got. They got 4.1. And then we make a little number line here. Or you could find concavity. It's going to be concave down because of the second derivative, so now you know it's a maximum. Or you could, a lot of people just like doing this and test it. Yep, it's a maximum. So that's the time. And how would you find the actual height? You got it. So you find S of 4.1, throw that into the position equation, and lo and behold, you get 182 meters. Okay, and then the last thing you had to do was to find, what do we have to find? The speed it hit the water. Stop, please. Okay, so speed it hit the water. Height is 0. We would take the height, we would set it equal to 0. So S of t, which was negative 4.9 t squared plus 40t plus 100. We would set that equal to 0 to find the time. And again, to save some time here, they did that, and they got 10.2 seconds. And then they plugged that back into the velocity equation and got a velocity of negative 60. So of course the speed would be 60. And it must be meters per second. Alright, that would be a wonderful free response question right there. Ties a lot of stuff into it, reviews the min-max stuff. Everything is right there. Alright, here's your assignment. Can I go on to the next page? We good with that? Page 347. So only the odd problems on this one, as always, as usual I should say. And you have a lot of time. You will get most of this done before you leave. Because remember, the very first problems, I mean if you go back and now you look at number 11, it says find the antiderivative of 5x to the 4th. So that you'll do in about 13 seconds, and then you move on to the next one. Okay, you're just going to rip off a whole bunch of them really quickly here.